The first condition that must be met for the mean value theorem is that it must be continuous on the closed interval of a to b. It can be any interval, right? A and b just are variables, but it must be continuous on these closed intervals. And the second requirement is that it must be differentiable on the open interval of the interval, right? So with these requirements, the mean value theorem that tells us that our average rate of change will be equal to our instantaneous rate of change. So here, let's take, for example, that we have the coordinate plane. This is our y-axis, and let me draw that better. We have our y-axis and then our x-axis, right? And we have some sort of function. Let's say we have, I don't know, something like this. And we know that our average rate of change for some value, let's say this is our a value. This is a. And then this is, let's say this is b. Right, this is b. So, first thing, the function is continuous, right? It's continuous. And it's differentiable, right? It has no sharp curves or corners or cuts. So it's continuous and differentiable. So if we were to find the average rate of change, right, for this point at point A, um, at point A, and with this other point at point B, right, we were to find this would be our secant line. We know that our average rate of change will be equal to some point in this function to our instantaneous rate of change. Right? Let's say this is our instantaneous or tangent line. And we can see they're parallel. They keep on going, right? So our slopes are equal to each other. So we know that for f of a, our change of y over our change of x must be equal to some sort of value of c for derivative of the function. However, in some cases, we may have where the a and b value are equal to each other. And that's where we get Rolle's theorem, right? So let's visualize this. So let's say again, we have another coordinate plane. This is our y-axis, and this is our x-axis. And let's say we have a quadratic, right? We have a quadratic in the first quadrant. And let's say this is our a value, and this is our b value. And we know that our a and b value will have the same y value. So because of that, because we know f of a will be equal to f of b, then our value, our c value for our derivative will be equal to 0. And this makes sense, right? Because these y values, we know that if we do a secant line, right, our slope is 0. It's a horizontal line. Then we know that our instantaneous rate of change will also have to be 0, right? And we can see that here, right? And they're parallel, right? Because the slopes are equal to each other. And rule theorem works when we have a max or minimum on an interval. So in this interval, we have a minimum. And that's how we can get that f of a is equal to f of b, right? Because they're equal to each other again, right? Because they're equal to each other, the slope is going to be 0, right? Because if we do f of a, our change of y, over our change of x, this will be equal to 0. And because this is equal to 0, we know that our instantaneous rate of change for some point on this interval, it will have to be equal to 0 as well. So now that we understand the requirements for a mean value theorem and what it tells us, let's apply this to some examples. Okay, let f of x be equal to x squared minus x plus 1. On the interval, we are told that the function is continuous on this closed interval and differentiable on the open interval. And it's telling us to find all numbers that C will satisfy the condition of the mean value theorem. So that's basically telling us for what values of the derivative function, right? So what value of the derivative do we plug in where it will equal the same value of our average rate of change? So when does our instantaneous rate of change equal our average rate of change with this interval? So the first thing we need to do, right, the first thing we have already done is we define it's continuous and it's differentiable on the interval we're given, right? So now we can plug in the endpoints, right? Because we're plugging in our a and b values, our intervals. So we plug in -1 into the function. We get -1 squared minus, we get -1 squared minus -1 plus 1. -1 squared is just going to be +1. Negative times -1 is going to be +1, and plus 1, this will be equal to 3. So then, if we do the same thing, but for our 4, we plug this in, we have 4 squared minus 4 plus 1. 4 squared is 16 minus 4 plus 1. 16 minus 4 is 12, and then plus 1 is going to be 13. So they're not equal to each other. So we can conclude that Rolle's theorem does not apply here. So now that we have points, right, we have -1, 3, and we have 4 of 13, we can find the average rate of change within these points. So we do our change of y over our change of x, we get -10 over -5, which is 2, positive 2. So we know, according to mean value theorem, that our average rate of change will be equal to our instantaneous rate of change for some sort of value. And that value is our C value. And we're trying to find what C equals where our average rate of change is equal to. So now we can find the derivative of this function, of the function we're given. So the derivative of f of x is going to be 2x minus 1. And we know this, right? We know this value has to be equal to 2. If we're trying to find the C value, we know that this must be equal to f of x must be equal to 2. However, we just have to find the x value, right? Because we know these are equal to each other. So we did 2 is equal to 2x minus 1, and we're trying to find x. So we add 1 to both sides. 3 is equal to 2x. Divide both sides by 2. We get x is equal to 3 over 2. So therefore, to satisfy the mean value theorem, our C value, our value that we input into the derivative, is going to be 3 over 2. And that is our answer. Because this value satisfies 2, right? So if we plug this into this, right? If we plug in 3 over 2 into our derivative, we will get 2. And we can check that by plugging it in. So if we plug in 3 over 2 into our derivative, we get 2 times 3 over 2 is equal to 1. And the 2's will just cancel, leaving us with 3 minus 1. 3 minus 1 is just 2. Well, you look at that. This is equal to f of 1 minus f of 4 over -1 minus 4. So we know for certain that our C value is equal to 3 over 2. And let's work on another problem. All right, let's say we're given f of x is equal to cosine of x. And the mean value theorem guarantees the existence of a value c over the closed interval of 1 over 3, of 1 of 3. And we have to find the c value that guarantees the existence of the value, right? So the first thing we have to do is find our points. So we're given that the function is continuous and differentiable on this interval. So we can find our points by plugging in this. By plugging in 1 is equal to cosine of 1. And we can do the same thing for f of 3 is equal to cosine of 3. So now that we have our point, right, we have coordinates, right? We can find our average rate of change. So we can do our change of y, cosine of -1 minus cosine of 3 all over 1 minus 3. Now this one will require a calculator, so I'll plug that into my calculator. So we can make sure when you're doing this into your calculator, you are in radians, because I was in degrees and got the wrong answer, but okay. When you're in radians, you should get negative 0.7651. Okay. So now that we know that, right, the mean value theorem guarantees some sort of existence for the c value. So we know that this must be equal to the instantaneous rate of change for some sort of c value. It must be equal to each other. So we can find the derivative of cosine, which will be equal to negative sine of x. And we know that f of x will be equal to this value. So if we set this equal to each other, 7,651, because that is our slope, right? Our average rate of change for the function at this interval must be equal to our instantaneous rate of change for some sort of value. Some sort of value. We don't know that yet. So then we can multiply both sides by negative to get rid of that negative, and we're left with positive 0.7651 is equal to sine of x. To separate x, we can do the inverse function of sine of x. So we can do inverse sine, or arcsine, it's also referred to, inverse sine. And we will plug that into our calculator again. I think you should get negative 0.8712 is equal to x, right? However, you must know, because it's a trig function, we know it has periods, meaning that it has the same y value for different x values. So we can look at this x value or c value, and we know that this isn't within the domain. So this cannot possibly be our c value. So to actually find the true period that this intersects our our function at the correct interval, we must graph it. So y, when we graph y of negative, right? So this is our x value once we plug this into our calculator. However, this is not within the domain. So we can plug this back into our f, right? We can plug this into our derivative equation. Negative 0.87112, and then this will give us negative sine of negative 0.8712 is going to be equal to 0.76514. And as we said, it's a trig function, so it has periods. It cycles. So this is not within the domain or the range of the function. So we have to find the intersection and find where this function, or I mean, this y value does intersect the graph at the correct interval, within the correct domain. So if we graph 0.765147, and then we graph our derivative, right? We get negative sine of x, and we look for the intersection. When they intersect at the interval that we want. Oh, sorry, this is meant to be a negative. So if we you can see that it intersects at 2.27 comma negative 0.765147. So therefore our C value must be equal to 2.27. And we can look at 2.27, and that is within our domain. So therefore this does exist within our function, and C is our answer.